Hello everybody. Happy New Year. It's New Year's Eve and I got a little time to play with what I like playing with. And back to the Manta project. Cool thing about manta rays, back when I studied them, I've studied ants and everything else. I love studying the way things work, but the thing with manta rays and birds and things that fly in the water, fly in the air, living creatures that have the ability to articulate everything about them. Okay, and so as we engineer off of wildlife and other things to do specific things, they do give up their secrets, and I'm going to do another video today on some of the secrets of the Manta, but to the Manta project. Today I'm going to discuss, I'm not going to actually show the propulsion system yet, but I want to start giving guys out there clues with Legioneering. Okay, and the reason we call it Legioneering is because it's a legion of people out there working on the same products. Okay, I mean, we copy from each other and we have ideas and we have improvements, and that's what we're all about. We work together as a community. People wondered, I'm not going to go too much in detail, but yes, I like to be paid on my own work that I provide, but there's so many people that have helped me through the years. This is the way I give back to the community. I'm not trying to sell you anything. I'm not trying to sell you a product. This is just strictly for educational purposes, to do with what you will. But hope this helps you overall. But anyway, I want to get back to Legioneering the Manta, and in this we're going to learn about propeller static thrust. We're going to learn about thrust increase. Thrust increase equals increased torque. Increased torque equals more kW load. Okay. The cause and effect, exploiting turbulence and wake fluid dynamics. In fluid dynamics, if you're dealing with water, you can't compress water, but you can have hard water. Okay, and the same thing happens with air. You can compress the air that's already compressed, and as you can ride in that hard air. Okay, hard air is we'll get into more of that later. The angle of attack, and when you're looking at this, you kind of, if you look out the rear end of a boat and you have that rooster tail coming up, the different angle of attack with power, tilt, and trim, other things are going on with that. But think rooster tail, and where you want to ride your propulsion is in that hard air, hard water rooster tail at the right angle of attack for the load that you're carrying. Okay. We're going to talk about the radius of propellers, the diameters, single blade, 2 blade, 3 blade, 4 blade, 5 blade, 6 blade, 7 blade, 8 blade, and 9 blade pitches, what they does. When you add a blade, all you're doing is adding thrust component. Okay. But again, as you add more thrust component, you're adding more torque, which is adding more kW load. Okay, so you want to balance the thrust that you need with your torque on the other end of it, because that comes down to energy consumption. We'll get more into the details on that. I work with Knights a whole lot. 369, Nikola Tesla taught me that as a kid. Okay, and I like working in those stages. We'll get into more of that. Ducted fans. Ducted is not anything new. There's other people who've done that. Coefficient efficiencies, velocity, stator blades, multi-stage 1/9, 2/9, 1/3, 4/9, 5/9, 2/3, 7/9, 8/9. Full stage is 9/9. Everybody likes to go with base 10 mathematics a lot of times, and that works for timing and everything, but it ends up with half stage, quarter stage, and with asymmetrical flight, the 9 base works out much better, okay? Just for teaching it and understanding it. One of the things in nature is suction has a relationship that's asymmetrical over pressure, and we'll get into that in future videos, okay? Thrust, drag, static, air intake, air exhaust, compression, thrust cone angle. This has been with air props. I understand it with water props, but the design with air props, that's new to me, and I'm going to probably make mistakes because I'm not as familiar with air props I am with water props, and I can't find the information to this day of what I'm looking for on that. And like I said, it's probably in my magic unit. Usually when I refer back to it, it all comes back there, but I have to usually find it first to get an exact handle on the what I call the slide rule. Okay, the airfoil, paddle wheel, torque, RPM, your density. Most everything that you design in aviation is designed at what they call standard air temperatures. Moisture has a big effect on the whole thing, so humidity does too. But we design around sea level and then work it on up to the different altitudes. Okay. The fluid dynamics, lift equals weight, thrust equals drag, center of gravity equals center of pressure. And a lot of people, when they're discussing aviation or teaching flight and stuff, they don't really discuss the center of pressure, okay? And the effects that you have when you're designing things. Center of pressure is one of the most important parts of it, okay? I'm going to talk a little bit, I'm going to touch base on the pumpkin seat effect, which has to do with the rooster tail, okay? And when you work it right, it's like pinching a pumpkin seed, because you're sending out a wave in front of you that actually breaks the wake like a geese flying in formation, and that little impact that you have up front makes a big difference of what's going on in the rear, okay? Some people call it training the air to do what you want it to do, and a little spot out there can make a big difference of what's actually happening in your airfoil, and that's part of the design too. Okay. Blade articulation, we talked about that briefly. Nature animals, they can articulate anything they want, and so we can take a fixed design, we can put movable control surfaces on it, but it's not as efficient as intelligent mind behind a body that can do lots of different things. So, think flapping bird wings, and hope you enjoy the presentation. And what is it exactly that we're trying to do with vertical takeoff and landing? Well, we've been doing it with helicopters for a long time. The problem with helicopters is not really much of a problem as long as you have static areas. But the noise that you have with a bunch of helicopters flying around is, dong, 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 dong. It has a specific frequency. But as far as efficiency, helicopter's pretty efficient design, and we'll get into that later and why, how that works. But what we want to do is do the same thing that a helicopter does, but do it safer, lighter, faster. Okay, I like to go fast. Okay. Anybody that knows me knows that I like to tiptoe, and when conditions are right, I love to go. That's just part of my personality. Can't help it. The basic design and layout that we did so many years ago, and how that all works. The Wright brothers had it right, and things that if you really analyze the Wright brothers plane, which is something I did way back as a kid, is they had it figured out based on 9, and if you take it out and draw it out in 9 sections, it becomes clear. But what they were doing is, at that specific part of the prop, is making the suction greater on the wings. Remember, they had heavy stuff. They didn't have things lightweight. Now we can go lightweight, faster RPMs. The thing is that when you go with bigger props, a slow-moving bigger prop is really the most effective way to fly, and it's quiet, but you always have a settlement of noise and vibration, so you can get those pitches up in a higher range that most people don't hear as much. It's not as disturbing to wildlife and other things out there. But the Wright brothers had their engineering right. I mean, if you look at it, canard, wing, propulsion, and their tail section, all based on things. But we basically take that, and if you'll notice, a third, a third, a third. Okay, 3, 6, 9. And if you divide things up, it's kind of neat the way that works out. The training aircraft, as we got into it being safer, most people feel that high wing aircrafts are probably the safest. For teaching landings and things like that, low wings are fine too. They all have their pros and cons. We'll get a little bit of that. But the first thing is you need to learn to fly a training aircraft. And Cessna 150 to me is one of the best training aircraft out there. Another good training aircraft that's you don't see too many of them, but was the Musketeer, made by Beechcraft, probably one of the best low-wing training aircrafts out there. But first things first, you got to learn to do it and be comfortable with it and the different things that happen in aviation, gaining experience and doing that. This is where we're getting into the wheel. And just something I want to point out, okay, is if you have a 10-inch diameter, okay, and you have a 10-inch pitch, okay, a standard propeller, in other words, you have 2 blades that, let's call that a propeller, and you have 2 blades that on each side, and you can divide that by 2, and but 10-inch propeller, this would be a 15-inch propeller, but it makes a whole lot of difference. Okay, 2 blades. In a 10-inch design, before the tips approach the sound of speed, the maximum RPM that you can turn those blades is 22,568.75 RPM. You go 7.76 RPM and you're getting into that speed zone. Now that's a really noisy prop, even if it doesn't have any pitch to it, because it's spinning at so many revolutions. Okay, from that you have 14.13 pounds of static thrust. In other words, 14.13 pounds is going to keep that buddy tethered. You go 14.1, it's going up. Okay, the static thrust in kilograms is 6.40. So for guys in other countries, the perimeter speed is 299.99. That's how fast that's traveling around that radius. Okay, to operate that with the torque and horsepower, it's and I believe in KW more than I do horsepower. Torque is more important to me. If you have the torque, the horsepower is there. But anyway, it's 5.743 kilowatts. The estimated flying speed with a 10-inch prop, in other words, that prop as it spins one time, one revolution that's moving 10 inches. In other words, it's 10 inches as it's moving one revolution. So half a revolution moves 5, 10, right? Got it? So that's what your pitch controls. And we'll get more into pitch and diameter flow and how to do props and layouts and simple stuff. A kid can do it, okay? So through that. Now we're going to change just one thing, okay? Notice your static thrust, okay? All we're going to do is go to a 1-inch pitch, okay? That's all we're going to do. With a 10-inch pitch at maximum RPM, the velocity for 10 inches is 213.7 miles per hour, okay? That's about 185.6 knots. Pretty rapid for carrying a very small package, okay? So we're going to change that to 1 inch, and look what happens. 14.13 pounds of static thrust. Is that right? 14.13 pounds of static thrust. 14.13 static thrust. Okay. So the static thrust stays the same. Okay. But look what happens to your velocity. It drops down to 21.3 miles per hour or 18.5 knots. So as far as climbing, it's not climbing very much, but your KW goes down. In other words, it only takes 3/4 of a horsepower, just a little above 3/4 of a horsepower, or 0.573 to lift that same 14.12 pounds. Okay, so just wanted to really point that out. Okay, as we're going through, we have the 4 major forces that act on an airplane in level flight, and that's lift, weight, thrust, drag, and your center of gravity and your center of pressure on the wing, okay? And then, of course, we'll talk about angle of attack and all the others. As you go faster, your angle of attack on your propeller is reduced, and as you go slower with fixed pitch prop, other things, your angle of attack increases. So with a fixed pitch prop, very simple stuff to figure out. Okay. Why did they build biplanes? Did they build it for structural speed? Why did they build triplanes? And if you really think about it, the Fokker D1, it had this other little wing up underneath here that was part of it. And notice that your wings are tapered compared to each other, and they're also staggered forward. And we're going to talk about that a little bit later too. Their control surface went past the wingtip. The bottom wings, they kept smooth, but you notice that they scalloped the back of the wing, and there's actually a reason for that, and that's something I didn't notice until this time around, until I saw Lillian scallop their wing. So a lot of these things that are out there that people are doing have been thought about by a long time. The tail surface for the DR1, lots of engineering went into that plane. If you ever seen somebody really fly a triplane that can climb like a bat out of hell, that can turn on a dime, very maneuverable airplane. And there's several reasons for that. The flow. Getting in the training aircraft, dihedral. If you have a wing that comes in the ground effect, the right wing has more effective lift than the left wing, okay? And so dihedral a lot of times was set up for auto landing and things like that. A lot of people don't realize that different flight characteristics, to where when you induce a roll, different things happen with the hedral. Just wanted to touch base on that for a second. The getting more into modern lift, we still have our weight, lift, thrust, center of gravity, center of pressure, drag. Okay, so when you're designing a propeller system for a thrust, you can increase your thrust by adding more blades to the propeller. That's what the wings teach us in that. And the manta ray, I'll show you later on how the manta ray gives us a secret of about how many props to put into the system. And so that's how we figured that out a long time ago, believe it or not. Okay. The modern aircraft, and with any aircraft, when you're thinking about setups, just reverse what the Wright brothers did and come it the other way, and you have a pretty much good idea. But there's a reason that your thrust cone is where it is in relationship to the wing, with other aircraft, whether you're running counter-rotating props, inboard or outboard, and there's different advantages to that configuration as well, and where you put that. So another thing to factor in when you're engineering something. You can look at other wing designs to where they have a big body wing, and then they come out on the wing tips and do different things in your aerodynamics. But the specific things of where you're putting things with proven designs, they all work within the 369 when you lay it out. So if you lay out with a 369, when you're blowing it up, you can, I mean, as far as sizing, you can come up pretty easily of what it's going to do. Thing is, as you increase your propeller, you increase more thrust, therefore you need more kW to operate it for speed. Okay? So it's give and take. It always is with engineering. You always have a balance. Whenever I'm engineering something, I have the fun of balancing low end performance coming out of the hole, mid-range performance, and then flat out top end and stability and holding together. So I love what I do on that. I've enjoyed doing that for years, and that's where I get my fun. Okay. So again, the Wright brothers had it right, because what they did is they took the wing force and they trained that air to hold closer where they wouldn't stall, and they reached the hard air. They trained the air between the two wings to do the airfoil of what it was doing. And this was a parallel configuration. Then later on, we figured out that we could change that angle, and instead of being parallel, we could move it forward and do different things with it. But you know, for first time out, they had some pretty good engineering that went on with that, and give us clues to how fixed stuff can work. We can make improvements. Okay, we all get comfortable flying the same thing, and you know the design. You know, just a few years ago we added the wingtips, and that came from us water people. Okay, boat people. I happen to be a pilot too. You know, flying, but we learned a lot about that with hydrofoils and the efficiency that the wingtips can give us. And again, you know, thrust, lift, weight, drag. Just want to touch base a little bit on the DR1, the manufactured by Fokker, and what they did. They took it to the extreme into that area. I hope you enjoyed this presentation. I hope it helps you with your designs and your ambitions, and understanding a little bit more about propellers and what 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 24 blades, 36 blades, you're adding to your torque. In the boating world, if you're under 1,000 horsepower, as far as your balance between speed and thrust, Um, um, the 3-blade is always felt my needs. If you go with a 4-blade, you're getting more thrust, but you're not really changing your speed, okay, at the same pitch. 5, same thing. So uh, uh, the it's just the amount of grab and torque that you're able to do with the different configurations on that, but you're adding more torque to that system. Torque equals kW, and so you're adding to the system. But in your proposed package, you do have to come up with the balance of everything involved with that, and you have to research and know the tricks of the trade of how it's done. So I hope you enjoyed your cup of coffee with me, and I hope you're having fun, because we are. And Happy New Year, everybody. Bye.